Our topic is all about Regula Falsi. The Regula Falsi method, also known as the false position method or linear interpolation method, is a bracketing algorithm or numerically solving equations of the form function of x equal to 0. This approach requires a continuous function over an interval a and b, where a root is known to exist. First, identify an interval a sub 1 and b sub 1 that brackets the root that is a function of a sub 1 and a function of b sub 1 have opposite signs. Then, draw a straight line connecting a sub 1 and function of a sub 1 and b sub 1 and function of b sub 1. The first estimate x sub ns1 is the x-intercept of this line. Determine the new subinterval a sub 2 and b sub 2 by replacing either a sub 1 or b sub 1 with x sub ns1, ensuring the root remains bracketed. In contrast with the bisection method, unlike the bisection method which uses the midpoint of the interval, Regula Falsi leverages linear interpolation to converge faster in many cases. Each iteration refines the bracket while maintaining the root within the interval, combining reliability with improved efficiency. This iterative process continues until the estimate meets predefined convergence criteria. So let us now proceed with the algorithm for the Regula Falsi method. So first, choose the first interval by finding points a and b such that a solution exists between them. So this means that function of a and function of b have different signs such that function of a multiplied to function of b is less than 0. So the points can be determined by looking at a plot of function of x versus x. Then, calculate the first estimate of the numerical solution x sub ns1 by using the formula x sub ns is equal to a multiplied by the function of b minus b multiplied by the function of a all over function of b minus function of a. So the third step is determine whether the actual solution is between a and x sub ns1 or between x sub ns1 and b. So this is done by checking the sign of the product function of a multiplied to f of x sub ns1. So if it is less than 0, the solution is between a and x sub ns1. And if it is greater than 0, the solution is between x sub ns1 and b. The fourth step is select the subinterval that contains the solution a to x sub ns1 or x sub ns1 to b as the new interval a, b. And go back to step number 2. Step 2 through 4 are repeated until a specified tolerance or error bound is attained. So when should the iterations be stopped? So the iterations are stopped when the estimated error is smaller than some predetermined value. So let's have here sample problem number 1. Find the root of the equation f of x is equal to x cubed plus 4x squared minus 10, and that is equal to 0 using false position method or Regula Falsi method. So first, we have to set x equals 0. So function of x, which is equal to 0, is minus 10. And again, we have to set x equals 1. F of x, which is 1, is equal to minus 5. And if we set x equals 2, function of x, which is 2, is equal to 14. Let's check for the sign change for the results of f of x, that is minus 5 and 14. It means to say that our interval is between 1 and 2 for our first iteration. For our first iteration, f of a sub 1 is equal to minus 5, that's less than 0, and fb sub 1, which is equal to 14, greater than 0. So the root lies between a sub 1 equals 1 and b sub 1 equals 2. Now let's compute for the value of x sub n as 1 using the formula a or a sub 1 function of b sub 1 minus b sub 1 multiplied by function of a sub 1 all over f, or function of b sub 1 minus function of a sub 1. So that is equal to 1 times 14 minus 2 times minus 5 all over 14 minus 5. The result is 1.26316. If we will compute for the value of function of x sub n-1, where x sub n-1 is equal to 1.26316, the result is 1.60224. It is less than 0. For our second iteration, function of x sub n-1 is equal to minus 1.60224, and f of b sub 1, or function of b sub 1, is now equal to function of b sub 2, which is equal to 14. The root lies between a sub 2, which is now equal to x sub n-1. The value is 1.26316, and still our b sub 2 is equal to b sub 1, which is 2. Now we have to compute for the value of x n sub 2 using the formula a sub 2 multiplied by the function of b sub 2 minus b sub 2 multiplied by the function of a sub 2 all over function of b sub 2 minus function of a sub 2. Substituting the values, x n sub 2 is equal to 1.33883. So computing for the value of function of x sub ns2, which is equal to 1.33883, so the resulting value is minus 0.43003. For our third iteration, this time our function of x sub ns2 is minus 0.43033, and our function of b sub 2 is equal to function of b sub 3, which is 14. So now the root lies between a sub 3, which is equal to x n sub 2 is equal to 1.33883, and b sub 3 is equal to b sub 2, which is equal to 2. So we can now compute for the value of x sub ns3. So 1.3383 multiplied by 14 minus 2 times minus 0.4303 all over 14 minus 0.43033. X sub ns3 is equal to 1.3855. To solve for the function of x sub ns3, we have the resulting value of minus 0.10995. So to continue our fourth iteration, so we have here f function of x sub ns3 is equal to minus 0.10995, and our function of b sub 3 is now equal to the function of b sub 4, which is equal to 14. Now the new interval is a sub 4, which is equal to x sub ns3 equals 1.35855, and b sub 4 is equal to b sub 3 equals 2. Solving for the value of x sub ns4, the result is 1.36359. And solving for the function of x sub ns4, the resulting value is minus 0.02706. Continuing the iteration up to 10th iteration. For accurate results, we can use Microsoft Excel. So based on the computation up to 10th iteration, the resulting value of x sub ns is 1.365230, with the resulting function of minus 0.00001.